Today we're going to talk about derivatives as functions, which is not really going to be too much different than what we've already done and is what we were getting at when we started looking at derivatives graphically. When we looked at derivatives graphically, we saw that we could take some kind of function, like a nice little parabola. We could graph its derivative. In this case, we saw that it looks kind of like a line. And so the original expression was a function, its derivative was also a function. So instead of finding the derivative at just a point, we could think of the derivative as a function itself that we could plug points into. So we have our two limit definitions of derivatives. Both of these definitions were finding the derivative at a point. So these were the derivative of f at a point A. So what I want now is I want a formula that's going to give me the derivative at any point x. And you might think we could just replace a with x, and that would be a reasonable thing to do. We notice if we replace a with x in the top formula, everything goes away in that first formula. So we get 0 over 0, and we're not going to be able to simplify anything because everything will cancel out. So if we're trying to find the derivative at a general point x, we're going to need to use the limit definition where h is approaching 0. Otherwise, the other function just doesn't help us. So we can just replace all the a's with x's. We're going to have f prime of x is the limit as h approaches 0, f of x plus h minus f of x over h. Cool. That's going to be the derivative. What we'll notice here is that the derivative itself will be a function. We're going to start out with a function. We're going to find its derivative. That derivative will be a function. If I want to find the derivative at a particular point, I'll just be able to plug it into that function. Okay, let's jump into an example. So if I want to find f prime of x, where f of x is x squared plus 3x, we're going to use our limit definition again. Or we're going to use our limit definition. We haven't done an example yet. So we have limit as h approaches 0, f of x plus h minus f of x all over h. Okay. F of x plus h, remember I'm going to have to replace all the x's in the original function with x plus h. So I'm going to have x plus h quantity squared plus 3 times x plus h minus f of x. Make sure you put this all in parentheses. That is the number one mistake that students make, is forgetting the parentheses there, because everything's going to get subtracted, all divided by h. And now we just have to simplify. So let's go ahead and FOIL the first part, the x plus h squared. This step is really just algebra, so we're going to have x squared plus 2xh plus h squared. I'll distribute the 3 to get 3x plus 3h. And now I'm going to distribute the negative sign, making both x squared and 3x negative, all divided by h. I'm going to hope that things cancel out here. The goal is always that everything that does not have an h should go away, so that we can factor an h out of the numerator. If things don't go away, that probably means you distributed your negative sign wrong. So let's see, we get the x squareds go away, the 3x's go away, and this is good. Everything left in the numerator has an h in it. So I'm going to be able to factor an h out of the numerator, which is good because that'll cancel with the h in the denominator. So when I pull the h out, I get 2x plus h plus 3. Cancel it out with the h in the denominator. Now as h approaches 0, we'll plug 0 in just for h. X stays behind, so we get 2x plus 3. Okay. So f prime of x here then is 2x plus 3. Okay. Using that formula, we can answer part B here. So part B asks for the equation of the tangent line, where we're working with the same function we did before at the point when x equals 1. We could use the limit definition to find f prime of 1, which will give us the slope of the tangent line. But we also know we have a good, nice formula up here that's going to tell us the slope at any point. We just have to plug our point in. So I can plug 1 in to this expression up here to get 2 times 1 plus 3 to get 5 is the slope of our tangent line. So once we have f prime of x, finding the slope of the tangent line at a particular point is pretty easy. I just plug that number in there. Okay, so 5 is the slope. We wanted the equation. So we're going to need a y value as well. So we're going to plug 1 back into the original function to find the y value. That'll give me 4. So I have the 0.14 and the slope of 5. So we're going to have y minus 4. is 5 times x minus 1. We could rearrange that. So y minus 4 is 5x minus 5. Add 4 to both sides, so 5x minus 1. Okay, you guys can look at the graph and make sure that indeed looks tangent to that parabola x squared plus 3x. Okay. I would suggest that you try this next example before you watch me do it. It's going to just be a lot more algebra again. So let's find the derivative here. Hopefully you're going to pause this before you watch me do it. And I'm going to find myself plenty of room here because I think this one might take some room. Okay, so find f prime of x using the limit definition. So we're going to look at the limit as h approaches 0. F of x plus h will be 1 over x plus h quantity squared minus f of x all over h. Oh, now I have to simplify this. I think you guys are going to be pretty good at this. We might have actually done this exact one the second day that we did limits algebraically, and we had that kind of joke problem. I think you did one exactly like this, and that was because I was trying to set you up for this particular problem. But practice it again anyway. So we're going to need to find a common denominator up here. My common denominator is just going to be x squared times x plus h quantity squared. So this piece is going to get multiplied by an x squared. We still have our limit out front. And then this piece will get multiplied by x plus h squared. And I'm going to go ahead and multiply all that by 1 over h just so I don't have the compound fraction here. Okay, so now just simplifying. So everything multiplied by x squared, x plus h squared. That h can move into the denominator. Then I have x squared minus this guy. I'm going to go ahead and FOIL that out. That is going to give me x squared plus 2xh plus h squared. All of that has to get subtracted. I'm going to be a little bit lazy here, and I'm going to go ahead and distribute the subtraction sign there and not write it in two separate steps. Okay. And so now let's see what cancels out in the numerator. X squareds cancel out. We notice that everything in the numerator still has an h, which is good. I can pull that h out. That's always going to be our goal, is to get rid of the h from the denominator, which means we want to pull an h out of the numerator. So I can do that. I'm going to be left with negative 2x minus h over this denominator. H's cancel out. And now when we plug in 0 for h, I'm going to have negative 2x over x squared times x squared. That's all going to simplify to negative 2 over x cubed. That is my derivative. It looks a little messy. We're going to learn how to get this without doing so much work next time, because that's a lot of work to have to do every time. Before we do that, we're going to get more practice using the limit definition. Let me give you some different notations. There's a lot of ways to write f prime of x. Sometimes we write this as y prime. Sometimes we write it as dy over dx. This is the derivative of y with respect to x. Y is my function, x is my variable. Sometimes I write it as df over dx. Sometimes I write it as d over dx, and then the f of x over on the other side. These notations we won't use so much. These are used more like in a Calc 3 class, sometimes physics as well. And then if I'm evaluating a derivative at a point, so now we have an a in here, sometimes I will write this as dy over dx with a bar, and then telling you that you're plugging in x equals a. Okay, so if we look at all these notations here, this notation d over dx of 1 over x squared, this is just saying find the derivative of 1 over x squared. That's what we did on the last page. So we know that that should be equal to negative 2 over x cubed. This notation is saying find the derivative of x squared plus 3x. That was the first example we did, so that's just 2x plus 3. This notation in part C is saying find the derivative of x squared plus 3x and then plug 1 in. Okay, so essentially I'm plugging 1 into here, which gives me 5 out. That's a number. Okay, again, the notation in D is saying I have the function 1 over x squared. Find the derivative of that, where x is the variable. So that's the same thing we got in the second example above, negative 2x cubed. And then again, part E again is saying find the derivative. So y prime means find the derivative. This is the same notation as saying f prime of x if we think about y being f of x. So again, this is what we did in the first example, 2x plus 3. Okay, so I'm just showing you that there's a lot of different notations. We're going to get practice with all these notations in class. I just want you to be comfortable with all of them because they are all used in different ways and at different times.